Thank you very much. And I'd like to thank the MRS for awarding me this very prestigious award that I'm honored to receive. Okay, so I'm going to talk to you today about some of the work we've been doing in Oxford, and actually the first slide it basically recaps the introduction, thank you very much, Amit, that you just gave, so I won't have to talk very much on it. But just to give you an idea of where I've come from with the research, I started doing my PhD in the Cambridge group under the supervision of Richard Friend, working on polymer blend bulk heterojunction solar cells. We called them solar cells, but I was using F8BT and PFB, and anyone who knows anything about those materials, they don't actually absorb any sunlight, so they were more like diodes, but they were quite interesting to look at. I then moved to Lausanne to do a postdoc with Michael Gretzel, and there I worked on solid-state dye-sensitized solar cells, and this really proved to be the platform technology from which I subsequently developed other structures and other devices, returning to Cambridge briefly in 2007, and then starting my own research group in Oxford from 2008 onwards. There I looked at mesoporous oxides blended with polymer semiconductors, and then onto more advanced structures of mesoporous electrodes. So the overriding sort of theme of my research up until 2012 was very much about how can you make materials that are very inexpensive but not very good semiconductors work well in a solar cell, and the theme was let's introduce nanostructure or mesostructure so that we can take two materials that don't work, stick them together and get an operational device. So that's sort of the backdrop to perovskite solar cells. So now I'm going to basically talk through first the history of perovskite solar cells. It's not very dense, but it's stretched actually over quite a long period of time. Perovskite itself is calcium titanate, which is this mineral depicted here, which has this ABX3 structure. That's an insulator, but any material which adopts this ABX3 structure or has components that have this perovskite octahedra are termed perovskites. The materials that we're interested in at the moment are metal halide perovskites. So the first report, I said it was over quite a long period of time, 1892, as far as I can find, is the first report on this cesium-lead halide materials. At the time of reporting it, they didn't know what the crystal structure was, and it took till 1959 to deduce it. So there's quite a slow start for this technology, if you like. In 1978, the first hybrid perovskite was shown, and this was by Dieter Weber, where they do the lead halide and the tin bromide iodide. Incidentally, this is the same year I was born. So whether there's any coincidence there or not, I don't know. Definitely not. This is during the sort of 90s, these materials were looked at for semiconducting properties. So there's another decade passed before something useful was done with them, let's say, or another 20 years. And there's quite a bit of work from David Mitzi and his colleagues at IBM and a few others looking at, for instance, this is looking at the conductivity in a tin halide, organotin halide material, seen a metal to semiconductor transition. It wasn't until 2006 to 2009 when these materials started to get put into solar cells. And this was the work by Tom Miyasaka and his PhD postdoc at the time, Akira Kojima, and they tried to use these methylammonium or ammonium lead bromide, lead iodized, lead chloride materials in a dye-sensitized solar cell structure. I'll come on to the architecture of the device in a short while. And they published electrolyte, or reported electrolyte devices in the Electrochemical Society meeting and solid-state devices, but their efficiencies were very low. Only about, 2%, that's not too bad, but less than 0.5% for the solid-state devices using polypyrrole, I think, as the whole transporter. So the first referee journal publication of these materials came in 2009 in a JACS paper where they got about 3.5% efficiency. And the strategy here is very much following the dye-sensitized solar cell. You start with a porous TiO2 material, and they coated the surface with a perovskite absorber that sensitized it. Light's absorbed in the perovskite materials, electrons transferred to the TiO2, and then flow out of the device. And the holes, or the positive charge left on the perovskite, is transferred to an electrolyte. So these work quite well, but there was a big downside that the electrolyte was corrosive, so the devices only lasted minutes, so they weren't very stable. And evidently, because of that, people didn't really follow it very much. I was actually in Japan as part of a collaborative project when this paper came out, and I sent a PhD student a year or so later out there to try to learn how to make perovskites. Unfortunately, Akira Kojima had left Tom Miyasaka's group and started working for his company, Pexcel, so was no longer doing this. Mike Lee, my student, managed to search him down in a bar in Tokyo, and has a note that I haven't managed to put up here, written on a back of a beer mat, of how to synthesize the perovskite. I think there was a critical mistranslation that turned out to be quite fortuitous that I'll talk about a little bit later on. So this is the device structure of what we try to follow. We take the fluorine dope, that's a transparent conducting oxide, coated in a compact layer of TiO2. This assures that electrons only flow out the bottom. And then it's a mesoporous layer of TiO2, and the green represents the perovskite. To coat the perovskite into this porous structure, we simply take a salt containing, in our instance, 3 moles of methyl ammonium iodide and 1 mole of lead chloride. And when you spin coat it and heat it, you end up with this mixed halide perovskite here, methyl ammonium iodide chloride. We tried a lot of different combinations of lead and tin salts, all the different halides, and this one, starting with lead chloride and methyl ammonium iodide, turned out to give very nice black or brown-black films that were pretty stable and quite smooth. So that's why we chose to follow that recipe. We then coat it with a hole transporter, a P-type material, and stick an electrode on the top. And that's the solar cell. Light's absorbed in the perovskite, electrons transferred to TiO2, transported out of the device, holes transferred to the solid-state hole transporter. And this is just the XRD pattern showing that this material is actually quite crystalline. So the initial operation, the first set of devices already beat our solid-state dye cells in labs. I think it was 6.1% efficiency. And this is a 7% efficient JV curve. So we already realized we were on something quite interesting here, and it was worth pursuing. One thing in all the studies we were doing on these devices, one of our toolbox measurements was to look at the charge extraction out of a solar cell. And here we pulse it with light and measure how quickly, or the transport lifetime, how quickly that charge is extracted from the device. And we can do that at different light intensities. So what we extract is a transport lifetime against light intensity. What we noticed with the perovskite sensitized devices were quite a bit faster at pulling charge out than the dye sensitized devices. So this led us to wonder whether the perovskite was conducting itself. So to simply test this, we took our normal device such a structure, but swapped out the porous TiO2 that's a semiconductor with this insulating porous aluminium oxide. And in this batch of devices, we put in 2 devices like this because we wanted to just see if there was any current and if we could do any transport measurements on it. And I think there were 60 TiO2 devices. And the first set of devices, literally the first JV curve, looked like this, which was a sudden jump up in performance and quite a surprise. Notably, we only scanned out to 1 volt because we never got higher open circuit voltages than this. So we haven't actually quite got down to 0 current there, which is also illustrating the high voltage of this cell. So suddenly, going from TiO2 to alumina gives a massive jump up in voltage of about 300 to 400 millivolts. So the explanation is that the perovskite is perfectly good at conducting charge, and there's no need for this porous N-type material. Now, we'd just done that, and we'd filed 3 patents on it, covering different aspects of the material in the devices on the 11th of May, and I suddenly noticed this paper on the 23rd of May, and my heart about doubled in rate as I quickly read through it and read through it again. I obviously saw a picture of a perovskite, efficient solid-state dye-sensitized solar cell, and I was slightly concerned. We'd just been scooped at the last minute. But actually, Kanitzidis, it's a very nice bit of work, but he'd done exactly the opposite. He'd used the 1890 material, not the 1978 material, the cesium tin iodide, and he'd use it as a hole transporter, not an absorber. So he'd left the porous TiO2, the dye, and he'd swapped out the spirometad, or the electrolyte, if you like, for this material, but also got working cells. So, but with that sort of fear injection, about a few days later, we wrapped up our paper and submitted it to Science, hoping we could get it out before anything else happens. Now, I was also in a European project, so this is sort of an illustration of competition brewing within the community, if you like. I was in a European project where we had a meeting about 2 weeks after we submitted our paper in Uppsala, and I'd been hanging on to this discovery we'd made and not reporting it to anyone. So I thought I'd present this stuff at this friendly meeting with my close collaborators and colleagues. It's just a small meeting. So I did. And of course, there were some colleagues from EPFL there, from Michael Gretzel's group. One of Michael's postdocs was there. And I sent Michael an email afterwards to sort of basically say we've had a big breakthrough. It's a shame you didn't make the meeting, but I'll update you when I go to Lausanne a few weeks later to give a viva. Incidentally, that same week, in terms of coincidences, Namgi Park had sent a student to Michael Gretzel's group with what the postdoc who was at this meeting thought was a new hole transporter for dye-sensitized solar cells, that Namgi Park had measured 9% efficiency in his cells, in his lab, and they'd already measured 7% in EPFL. So I thought, oh, well, that's interesting. Never mind, it'll get blown out of the water by the perovskites when we get through. I went to Lausanne a few weeks later, and after I'd given a presentation, Michael subtly dropped that they also had 10% efficiency with perovskites. That took me a little bit by surprise, and a few days later, on the 5th of July, they seem to have submitted a paper that got rather more rapidly through the reviewing process, should we say. So this one was published a month afterwards on the 5th of August. Now, they had only done the TiO2 sensitized cells, so still a very great achievement, nearly 10% efficiency, but they hadn't moved across to investigate if you can get rid of the TiO2 with alumina. So our paper was then published a little while later in, I think it came out in November or October. So that's sort of like the sort of early history of now we've really got something we need to work for. And in our first paper, we've got this mesoporous TiO2 cell. We've got these mesoporous alumina cells that give the higher voltage. But we also had a little play around with, do we need the mesostructure at all? Can we get away with just a flat absorber layer of perovskite? So to investigate this a bit further, we took, this is an SEM cross-section. I don't know if you can see it very well, but this bobbly bit in the middle is mesoporous alumina, and it's infiltrated with perovskite. So you can think of that as a uniform composition. We tried thinning down the alumina to see what happens. And in this instance here, you can see there's a solid layer of perovskite on top of the alumina, and then just the flat film. So if we need this mesoporous film, the thought is we need the high surface area to get the holes out of the material, then the current should drop rapidly as we go in this direction. Actually, what we saw was the opposite. As we go to these thin films, the current increases. So staring at this SEM here, you can see there's a big thick slab. It's about 300 nanometers thick of material that's clearly generating charge. So what this means is either there's excitons in this material that can migrate to the heterojunctions with high mobility, or it's just a simple thin film semiconductor. Now this actually took me a few weeks to get my head around, having spent about the last 12 years of my life convinced that nanostructure and mesostructure is important and trying to make all sorts of elaborate materials. Now having to move on to thin films, I wasn't willing to give up straight away, but actually that's pretty much the way we've gone. And one aspect that's really important is how long do the charges live before they recombine to enable a thin film device to work. And what I'm showing you here is the photoluminescence decay of the material. So this tells you how long does it take before the electrons and holes recombine and re-emit light. And with our mixed halide perovskite, it's a few hundred nanoseconds, about 300 nanoseconds. And if we contact this thin film with an N-type or P-type material, the photoluminescence is quenched very quickly. So it's quenched because the charge can flow out of the perovskite. They're no longer there to recombine and emit light. So we see this rapid decay. And by modeling with a diffusion rate, the difference between the non-quenched and quenched samples, we can get a diffusion coefficient and extract a diffusion length. And we find the charge can move around a micron in these films. So you only need a film around 300 nanometers thick to absorb almost all the light. So at 1 micron, that's suitably long to enable very good operation. And this, I won't go into the details, but this is very much a lower estimation of the diffusion length. So it's likely it's at least a micron, and it may well be tens of microns, maybe even more, when we finally optimize the materials. So why did we get sort of lower voltage and fill factor in the thin films? Well, the simple answer is the morphology of the materials weren't very good. So if you look at the SEM images here, this is the perovskite in dark coated on porous alumina and the perovskite on a flat substrate. You get these ginormous crystalline platelets, tens of microns in size, but they've got massive holes between them. So we somehow needed to improve the uniformity of this. So we look back in the literature. You have to go back a few years. You can't just look at the previous couple of years. But in 1997, there was a nice report of co-evaporation. We happened to have an organic vapor deposition chamber that wasn't being used very much in the lab. So we tried to follow this approach. This is the 2013 diagram equivalent. And what we tried to make was basically a flat junction device with FTO, the N-type contact, TiO2, the solid perovskite layer, P-type contact, a metal electrode. So in terms of film uniformity, this is the cross-section of a solution cast film at the time. I will note that this has been much improved now, but at the time it was very rough. And this is the vapor deposited film. So it's orders of magnitude less rough and clearly should work well. So I'm just going to show a slide that I've shown a few times before, which is how the efficiency improved over time. This was a PhD student starting here. And within about 4 months, she'd managed to get the efficiency up to 15.5%. That's a pretty quick increase on anyone's standards. So it does work. The thin films do work. There are still some issues, but they're generally, the concept's good. So this is just a picture of a nice, smooth, relatively large area, evaporated perovskite film. That's not a device. That area is not 15% efficiency. Don't be misled. Okay, so just to sort of have a look at some of the subtleties of solution processing these materials. We start from a salt. We have to dry out the solvent. In our recipe, we've got excess organic as well. And then we have to heat it, and it has to crystallize. This all happens at once on the substrate. It's not that easy. And what usually happens, depending on the temperature of the anneal or the thickness of the film, you end up with more or less holes, bigger domains or smaller domains. And we did a mathematical model to predict this based on mass loss and kinetics and de-wetting of the substrate. And we came up with a contour plot that looks something like this. And basically, if you go to thick films at low temperature anneals, you can get close to complete coverage. So this is sort of one of the champion devices from our lab, the sort of efficiency you can actually get from a planar junction solution process device, where if you scan on the reverse scan, it's about nearly 18%. On the scan coming back here, it's coming out lower. I'm not going to go into the details. This is hysteresis in the JV curves. I won't go into the details in this talk, but it's certainly a current topic in the field. Where does this come from, and how do we eliminate it? But encouragingly, if we sit near the max power point on this JV curve here, we find the current stabilizes at a good high value, and the efficiency stabilizing a little over 17%. So it's a bit lower than the nearly 18% of the JV curve, but it's not far off. We think this is the root of this, we believe, is ion migration and from some mobile ions in the film. So improved crystallinity, improved processing, and improved contacts is going to continue to improve the hysteresis, if you like. So just taking a step back from that, once we realized that the thin film really works, we don't need to sinter the perovskite at all to high temperature. So basically this opens, it only gets dried at 100 degrees. So it pretty much opens any P or N-type material that can be made compatible with the perovskite will work. So we went through, we screened a load of materials that had been used in the organic PV community to see what was a good P-type and N-type material. And PCBM, this C60 fullerene derivative, is a good N-type. P.PSS, which is this cheap conducting polymer, is a good P-type. And these solar cells we can make like this. This is a cross-sectional SEM. This is actually coincidental, but it's almost the identical structure that Alan Heger reported in '95 from the organic PV community. And there we're simply replacing this P3HT PCBM bulk heterojunction with a perovskite C60 bilayer. These solar cells worked similarly at the time to the regular devices. Just to confuse everyone, we called these inverted. In the organic PV community, they call this structure regular and the other one inverted. So now we don't know what we're talking about. But especially because most people working on this now are from the organic PV community. And this is possibly the photograph of the first flexible perovskite solar cell. Of course, they're all low temperature process. And that worked on ITO the same efficiency as on the glass ITO. So it now opens up prospects for doing this on flexible metals or plastics if desired. So another application is building integrated photovoltaics. This is certainly something we were pushing for hard with the dye-sensitized solar cells. And when we started working with perovskites, there's a slight inconvenience that they're brown. So now I'm sure you could sell it in some countries. If we make them thin, we can claim they're bronze or sort of orange, and that's got a certain appeal, but it's not ubiquitous. If we want to make the future cities look something like this and all the buildings generate power, then we need to do something else to try and make them compatible. So we went back to this study on de-wetting and wetting and surface coverage and intentionally processed the perovskite films so they form lots of little islands. So if we do that, we can control the average visible transmittance through the active layer. And because we still have our N-type material and P-type material, even in the regions between the islands, we still have a diode. It's not quite as good rectification as when we've got the perovskite there, but it's still a diode. So these work in solar cells, and they're on the order of 5% efficiency, 5 to 8% efficiency, depending on the transmission through the device. It's not great transmission because we're using gold electrode there that's not noted for its semi-transparency, but it illustrates the feasibility. The other nice thing is we can dig our dye out from the cupboard and stick it back in the hole transporter if we want to tint these cells. And then in the gaps between, we can basically control where in the color quadrant we go by putting a pigment in. So it's a way of introducing structural color in a sense by having holes, and then introducing further tints by putting in pigments that you know are stable. This is a dye. This isn't what you'd use in a proper, if you actually wanted to deploy this, you'd use a stable pigment. Sort of going on a bit further, we can actually try to do this in a more controlled way. And this is just a cross-section. It's basically a nice image of a perovskite film where we've used a template that we've used polystyrene spheres to template. And then we filled this little cup of silica with perovskite that's highlighted in purple. And then our hole transporter goes on the back. So this has a similar effect of creating semi-transparency, but with controlled domains. Okay, so another aspect that people talk about quite a lot and that is a concern, we do have lead in this material. There's potentially toxicology issues. I'm not going to stand up and say whether it really is an issue or not. We clearly have a lot of lead deployed. It's a very small amount in these solar cells. But that still gives motivation to try to find other materials, other metals that work. Tin is the next obvious choice. So we investigated this and could make methylammonium tin triiodide quite easily. This is the powder XRD, and this is the reduced crystal structure. And then what we find is the band gap shifts out to lower energy. This is the PL here. So actually, this gives us quite a lot of additional tunability in the band gap by taking tin and, for instance, mixing with lead. You can tune between. These devices worked, if depending on your definition of worked. The best efficiencies were about 6%, but I show the whole spread of data, so I'm not trying to dress this up as more than it was. It demonstrated that a non-lead material could give a decent device. It also demonstrates there's a lot more work to do with tin if we want to move away from lead. But what is actually peculiarly interesting is the open circuit voltage for this device was about 0.88 volts for a 6% device, and the band gap's only 1.23 EV. So even though all its deficiencies and variation, the voltage loss, or the voltage deficit between band gap and VOC, is only 350 millivolts, which is actually for very similar, if not a tiny bit better than crystalline silicon. So if this can be made to optimize well, it may be better material than our tin material in the solar cells, our lead material. The final technical thing I want to show is just mention a few words about stability. That's the other aspect. So the efficiency is skyrocketing. The lead may or may not be a problem. Stability is the other thing we need to address. This just shows some cells. It's data we took a little while ago. Some solar cells with the porous alumina that are sealed in nitrogen, and the current's more or less stable under full sunlight with UV component generated from a xenon lamp, but it's only at 40 degrees C. Now, when you heat these films up in air, something quite catastrophic happens. The perovskite that's black turns to lead iodide that's yellow, so there's a degradation in the thin film. Now, in the bulk, this shouldn't happen until around 300 degrees, but it's catalyzed by moisture in the air, and in the thin film, because you've got a much higher surface area, the temperature of this transition comes down to 80 degrees in air and about 150 degrees if it's in nitrogen. So it still happens. Now, it may not be critical without the moisture there, but if you can protect it to a certain extent with something like simple, like PMMA as a polymer, then this doesn't happen even in air. So it's quite stable, and there's no evidence in the XRD of lead iodide there. So what we can do, instead of just using the whole transporter, the P-type material, to conduct charge, we now have to think about designing it so it actually enhances the stability of the perovskite as well. It's our first layer of defense against degradation. So we followed something we've been working on previously using carbon nanotubes and embedded them in a PMMA matrix. This is the schematic of the cross-section of the device. Here, where the nanotubes and PMMA are mixed together as the whole transporter. And we found these devices worked. The best efficiencies were around 15% with around 10% average efficiency. So these can work as a good whole transporter. And very importantly, before and after heating, so these are made fully functional solar cells, just put on a hot plate in the lab at 80 degrees for almost a week. Basically, before and afterwards, there's no difference. This is not a standard IEC test. This one definitely isn't a standard IEC test. We don't have an 85-85 chamber in lab, so we thought we'd just put it under the tap. This is a perovskite solar cell with water flowing on it, so with the PMMA coating. So that's the top side where the PMMA is. So it's not water soluble when it's properly protected. If you do this on the film with, sorry, I shouldn't have bothered trying with this thing. It's gone a little bit haywire. If you do it without the PMMA layer on there, or the PMMA and nanotubes in this case, it goes yellow the instant the water hits it. And this is the performance before and after our water flowing stability test. So I've given you a sort of a run through of some of the key breakthroughs we've made in the lab over the last year or two. There's been a lot of other stuff going on. These are the papers published in 2013. There were about 60 papers published in total. I think about 20 were from my group, so there's 40 others. And in 2014, it's already gone up to about 400. So and by the end of the year, I guess this will be 600. Next year, we'll certainly be looking in the thousands. I don't know how many. Let's see what happens. What's this driven? This has driven advanced technology in Oxford, but also the rest of the world. And there's been some fantastic results from some Korean groups really pushing the efficiency. So we now have certified efficiency for perovskite solar cells in excess of 20%. So this is really putting it right in there with the thin films. Can it go higher? Is it going to go up and plateau out with SIGs and CAD-TEL? Obviously, I don't think so. So I was just searching the internet for pictures, and I saw this one, and I thought I'd just chuck it up to see if but that's not my opinion, but you never know. Can perovskites beat silicon? Or what will happen? So I'm just going to look, I'm not going to go into detail. This is a lot of different steps in making silicon ingots to wafers, and then you've got to make the wafer into the cell. The perovskite's relatively simple. You start with a yellow powder, mix it with a white powder and a clear liquid, and then coat it with a few other layers of the P and N-type materials to make a thin film. But it would be naive to think that means with the same efficiency we'd definitely win. We've done a little bit of a cost analysis. This is, I say don't quote me on this. It probably will be quoted, but they're a little bit more in-depth than back-of-the-envelope calculations, but of course you don't know how much it costs to make a solar technology until you've actually set up the factory, and we're a long way off that at the moment. But basically, this is the breakdown of the materials, the perovskite at research scale. So this is what we can buy stuff for today for certain materials. The perovskite's only about $1.33 per square meter. So if we assume we've got a 60 to 30 megawatt factory, that's only actually $1.28 depreciated over 7 years for a gigawatt factory. So you're talking about 25 cents to 18 cents per watt peak, depending on a 15 or 20% module. And that's at research scale. We can genuinely buy these materials at these prices today. Now, there could be other stuff that goes in to make it more expensive. But that we still can't rest on our laurels, because look at what silicon's done since 1977. It's just come down and down in price. And now it's certainly the module price is below the cost of generating electricity from oil. Of course, in some locations, of course, you also have to do something with that electricity. It's not produced on demand. If this could be reduced by another factor of 4, that would compensate for the extra cost of storage, and then PV could really compete with power. One way to do that is to make a tandem device. So crystalline silicon's down here, but what we need another, this is absorption edge, we need another material somewhere in the middle that's a good solar cell with an intermediate band gap, so that we can absorb the blue photons in the top cell and the red photons and the IR photons in the silicon. This is a lot of other technologies, and what I'm showing here is operational loss. So this is the difference in the voltage at maximum power point to the band gap of the solar cell. And this basically gives you your energy loss in extracting work from the solar cell. Silicon's got a relatively low loss, but everything follows this empirical trend that there's no necessary understanding of. It just seems to follow it, that as you go to wider band gap, the loss increases. Perovskites are already bucking the trend, that they're coming down here as we improve the technology. The operational loss is getting very close to these existing lower band gap materials. And in principle, if we can push it down a little bit further, it'll end up sitting on this line, and it all looks set that it's going to be comparable to gallium arsenide or gallium indium phosphide. In addition, I'll just show you on the next slide that the perovskite's quite tunable. So in principle, once we've got the low losses, we can tune the band gap to try to make it optimum for a tandem junction cell. And this is just showing you the example of mixing iodine and bromine in a 4-mamidinium-lead perovskite. And by doing this, we change the lattice parameter from around 6.3 to 5.9 angstroms. And this gives you a change in the band gap of the semiconductor. So we can go from black to yellow. So before we try to confront silicon, we should try to enhance silicon. And this is the strategy that could be quite useful, where you can put a perovskite cell on top of crystalline silicon. And certainly if the lab-based efficiencies now being reported could be translated into wafer-scale device efficiencies, that would already boost a 20% silicon wafer. So I've still got a few minutes, actually, so that's all right. So why are organic-inorganic perovskites such good solar cell materials? One aspect is their energetic disorder. So what I'm showing here is the absorption coefficient that's determined from photothermal deflection spectroscopy against the photon energy, so the band gap energy. And the slope of this tells you to a certain extent how much disorder you've got in the tail of your band edge. And the more disorder, in principle, will lead to a lower voltage in the solar cell. Down here, I plot, something's fallen off the bottom, the different technologies and this Urbeck energy. This Urbeck energy basically relates to the steepness of this slope. The smaller the Urbeck energy, the less the disorder. And you can see gallium arsenide is only 7 millieV. Silicon is 11, but it is an indirect gap semiconductor. And the perovskites are around 15. This compares to around 25 for SIGs. So it's closer to these crystalline materials than it is to the polycrystalline thin film. Notably, the lifetime is also rather long in this material, the carrier lifetime. This is something that you may or may not be able to get your head around. What I'm showing you here is the electroluminescence from a device against the energy of that electroluminescence. And I'm also showing the EQE, the spectral response of the solar cell. The electroluminescence peak represents the average energy at which the electron and hole recombine. The absorption onset represents the minimum energy you need to generate charge. So the closer this EL peak is to the absorption onset, the less intrinsic loss you have in your material. And this is only valid when you're in the radiative limit. So it assumes that you've switched off all non-radiative processes. So when you've perfected the material that you've got no recombination via traps or defects, this is what matters. And you can see perovskite is again in quite a similar position to gallium arsenide, not quite so good at the moment. Organics, there's a bit of a gap there, and SIGs has also got a slow absorption onset, as is silicon compared to the EL peak. One thing that's actually quite interesting here is cadmium telluride, and people have always, it is a very good technology. The problem with CAD-TEL is it's not very radiative, so most of the recombination isn't at this energy, it's at a lower energy, either here or below. But if that could be switched off, I mean, it's what people are trying to do, pacify all the defects and traps. If that could be switched off, CAD-TEL would also actually be extremely competitive to gallium arsenide. Of course, it's got cadmium and tellurium that might not be ideal, but I can't really shout about that because we also have lead. So, another aspect that's very interesting, and again it relates to this radiative limit for efficiency. When electrons and holes recombine in a solar cell, or at least when a solar cell material absorbs light, the fundamental laws stipulate that electron and hole has to at least be able to re-emit light. If you want to absorb strongly, you have to emit strongly. Everything else is additional. So if you've got non-radiative recombination channels, there are extra losses in the solar cell. So your material will get as good as it gets when all recombination is radiative. And what we find for this perovskite material is the PL quantum yield can get up to around 70% efficiency. It's more typically 40 or 50, I will note, but it can get up very high under high excitation. But under lower excitation, more comparable to full sunlight, it's only 30 or 40%, still very good, but this implies that there's relatively little non-radiative losses, relatively little trap-assisted recombination in this material. Because of this property, we can actually even observe lasing in this material if we just stick it in an optical cavity, and this is relatively simple. So that is surprising for a solution-processed crystalline material. Something else that this material is polycrystalline, and for cadmium telluride, the grains and defects at the grains is a big problem, and you have a big potential barrier. Now this is for an passivated cadmium telluride film. If you use cadmium chloride or magnesium chloride, this barrier drops to a few hundred millieV. SIGs, which was deemed the wonder material, has only 100 millieV barrier at the grains. These are some measurements from David Kahn and co-workers of some surface Kelvin probe measurements, and they find the potential barrier in the triiodide film is 60 millieV in the dark and 15 in light, and the methylammonium iodide chloride, or the route from chlorine, gives almost an unmeasurable barrier height. So it seems like there's very little barriers at the grain boundaries. On top of that, we've got this is a single crystal platelet here, cross-section through it. The crystalline domains are much larger than the film thickness. So we've got nice crystalline materials. It's almost, but not quite, like a single crystal. In fact, we do know that there are issues with the grain boundaries. They're just not totally detrimental. But moving away from a polycrystalline film more towards a single crystal film will definitely be the route forward to get much higher performance. So I just want to finish with a few words on our commercialization activities. So we filed about 20 patents in perovskite solar cells, or 20 patent families that are licensed exclusively to Oxford PV. That's our startup company from the research group. And in Oxford PV, the target is to develop a stable material set, to develop the processing methodology and know-how to be able to manufacture this stuff, and partner with a manufacturing partner, or partner with someone, for instance, who's already making silicon solar cells for that application, delivering a material set and the know-how. And also we're in a lot of discussion with tool manufacturers to try to deliver, in principle, a turnkey solution or turnkey adaptation to an existing silicon PV line to try to make them into modules. And I probably shouldn't put up a time, because almost certainly it'll be different, hopefully sooner, but just so you've got an idea, we do plan to have a first product in 2017. Some people might say that's not ambitious enough, but there we go. A key thing, what stands between us and that product in 2017, certainly proving the stability. So we're doing a lot of work on following this thin film certificates test on 20 by 30 centimeter mini modules, and examples of the sort of things modules need to get through is 85 degrees, 85% relative humidity. For this test, it only has to do 1,000 hours, but I really think to get comfortable that this is going to last on a rooftop, it probably needs to be closer to 3,000 hours with relatively little decay. Thermal cycling, 200 cycles of plus 85 to minus 40. Now, if you've got a material that has a phase transition in that range, you probably want to think carefully about it. So we're certainly doing a lot of work to make sure that's not the case in these materials. And full spectrum light soaking. So we light soak with the UV light included, and in fact there's an additional high UV exposure to make sure these things are going to last under sunlight. You could argue that you might be able to introduce a UV filter on the device, but we want to try and get through without that need, because that will also require the UV filter to last for 25 years without degrading, if that's what you need, and it adds additional cost. So if there happen to be any investors in the audience, I'll do an unashamed pitch that please contact me afterwards. We're always looking for money, because that's the second thing that stands between us and our product in 2017, is quite a bit of investment. So to summarize, I've talked quite a lot, so I thought I'd just put one slide up to sort of summarize where this stuff's come from and where it might go. And of course, this is objective. This is my opinion, if you like, but based on all the research we've done. There's really 2 or 3 device architectures that are currently making very efficient solar cells. One's based on a thin TiO2 layer that's infiltrated and capped with perovskite. So we've got a solid absorbing layer of perovskite, we've got this thin porous TiO2. The reason why the porous TiO2 is advantageous is it helps extract charge at this contact. The other structure that we were looking at mainly was the porous alumina on top of, filled with perovskite and capped with perovskite in the most efficient devices. That also helps to make uniform films and aids a little bit in the charge extraction, not because the alumina is conductive, but we get a slightly different material in this porous alumina. So we actually have a slight bit of end-doping, which I won't go into. But both these technologies, the porous structure is getting thinner and thinner, and pretty much it's going to end up as this planar junction device. And the reason why I'm pretty sure of this is that the properties of the perovskite film, the larger the crystalline domains are, the better the properties. The higher the mobility, the higher the photoluminescence efficiency, and basically the better quality of a semiconductor it is. The crystals within the porous templates are very small, so they've got high surface area, and they're not as perfect. So I think everything will condense down to this structure, and then there's a lot of different choices of electrodes, some coming from organic PV, in principle some coming from thin film, and then we can look to combine it in a hybrid structure with either silicon or thin film, and then eventually, when we've got a low gap perovskite and a wide gap perovskite working, we'll be pushing forward for tandem all perovskite devices to try to get greater than 30% efficiency. So I'd just like to acknowledge my research group and collaborators, and also funding, and certainly not last but not least, I'll thank my PhD supervisor, Richard Friend, for starting me off on this path and really encouraging me in research. And I'll thank Michael Gretzel as well for introducing me to the dye-sensitized solar cells, and being a great supporter throughout my career, and now really driving me forwards with very, very strong competition as well. That's always important. And Mike McGeehee as well, who actually nominated me for this award and is an equal inspiration in his research. So, and thank you very much for your time.